All right, yeah, so I'm Jackie Young from Stanford University, and on behalf of my co-author, James Landay, I'm here to present our project, InfoLED, Augmenting LED indicator lights for device positioning and communication. So we have a lot of AR devices these days. AR devices allows us to do spatial mapping and understanding of the real world. However, they usually treat electronic appliances no different than just ordinary objects. To tackle this problem, we propose InfoLED to allow smart appliances to be easily incorporated into AR. InfoLED uses indicator lights that already existed on many appliances, and we overlay high-frequency luminous flickering without disturbing the original functionality as the indicator light. The indicator light can still display different colors and patterns as shown in the video. Our experiment shows that InfoLED can be recognized from up to 7 meters and do not interfere with users' ability to read the original pattern. So I'm going to first start by talking about related works. So traditional device tracking system can usually be divided into 3 categories. The first category uses vision-based approach. They usually require change the look of the appliances, or they cannot distinguish appliances of the same make. For example, in this case, some kind of AR sticker is attached. Later research fuses data from multiple sensors to disambiguate similarly looked appliances, but they require the appliances to have a fixed location. Wireless-based approach, such as using Bluetooth or ultra-wideband, cannot provide positional information, or they have limited accuracy. InfoLED is kind of the work that falls into the category of LED to camera communication. So this is our work is not the first kind of work in this category. However, prior work in this area usually focus on increasing the data rate and usually leverages spatial domain to encode information, which limits its working range, renders it unusable for AR applications. InfoLED, on the other hand, encodes data onto the time domain so that it can be recognized from far away. So now we'll talk about how we design InfoLED to achieve all this. First, we'll talk about the appliance end of the system, which is the firmware that have to be applied to appliances so that it can encode the actual information onto the LED to facilitate AR interaction. So this part of the InfoLED needs to transmit identification and debug information for AR applications. It also needs to coexist with human-readable information so that the original functionality of the indicator light won't be disturbed. Also, it needs to be decodable by an off-the-shelf smartphone from a distance. So therefore, we designed the encoding pipeline like this. So as I said before, InfoLED encodes data onto the time domain. So each data packet, we transmit data into data packets, and each data packet has 16 bits of payload, carrying debug and identification information. For those 16 bits of payload, we use Manchester code to encode them into 32 symbols. The reason why we adapt Manchester encoding is because it allows us to maintain any given average brightness for displaying any given pattern and color. We also have 2 bits of hash to verify the integrity of the payload transmitted. And finally, we have a specially designed 10-bit preamble so that, and this specially designed 10-bit preamble won't collide with any data transmitted with Manchester code so that we can transmit any arbitrary payload with this preamble. The entire packet is transmitted at 120 symbols per second, which make the flickering close to the human critical flicker frequency, and yet decodable by a commercial smartphone, which captures frames up to 240 frames per second. The resulting data rate is 44.4 bits per second. Next, we're going to talk about InfoLED scanner, the scanner app we built so that it can recognize information and then track the InfoLED. The scanner, our scanner app needs to be able to locate InfoLEDs with a sequence of captured images. You also need to be track multiple InfoLEDs because it won't be useful in an AR environment if you can only track one InfoLED. And also it can decode information from InfoLEDs. So let's first see how the scanner locates the InfoLED. The scanner captures images at 240 frames per second. Let's take a look at 2 consecutive frames the scanner captures. And let's take a look at the region of the image where the InfoLED resides. So there are 2 InfoLEDs. As we can clearly see, the difference is you can see that because InfoLED is changing brightness rapidly, the 2 consecutive frames have different brightness on the InfoLED. So therefore, a really easy way to find the InfoLED is just to take a difference between the 2 frames. Here you can see the position of the InfoLED is clearly visible in the blue circle. However, since the viewport of the camera can be absolutely stable, the user is still using the phone to do many other things. This method also highlights edges of the object in the image, showing red circle, which is not desired. So therefore, what I actually do is we take the image, we slice it up into 8 by 8 blocks so that this processing can be parallelized on GPU. We match each block with the corresponding block from the previous frame. And then, because we measure most of the other, we assume most of the other object will have somewhat consistent in brightness. So we can move the block a little bit around to find a spot where the difference is minimum. So with this, we basically remove those motion artifacts. And then we compute the difference block by block, similarly as before. And then we get the motion compensated difference. In this motion compensated difference, we can clearly see that the InfoLED is still there. It still can be detected. But because we move around each block a little bit, this is basically similar to optical flow computation. With this, we can remove the artifact caused by motion. And after that, we apply a threshold so that we can get a binary image with the InfoLED highlighted in bright spots. And however, the InfoLED will not change its brightness every time. As I said before, like for example, the InfoLED changes brightness probably 1 to 4 frames in terms of camera frames. So in some of the frames, we may not get a bright spot because the InfoLED is not actually changing in color. So therefore, we compute a sum over a sliding window of frames, and so to keep consistent tracking of the InfoLED. The entire pipeline is done on GPU on a mobile phone, so that we can do this entire thing quickly and efficiently. So let's go back to look at the big image. In the entire image, the scanner might detect multiple InfoLEDs, right? So because InfoLED requires us to track it for a period of time so that we can decode the signal, we have to be able to track each individual InfoLED and where it is at every given frame. The way we do that is we have a few detected InfoLEDs. We also have a lot of previously detected InfoLEDs. This is combined with their historical brightness. The goal is to match each detected InfoLED with their history positions so that we know which brightness history this InfoLED should append to. A detected InfoLED may also be a false positive. It could be caused by rapid motion, or it could be caused by another object that is changing in color. Changing in brightness. So in that case, we match the detected InfoLED with a copy of themselves called discarded InfoLED. Each detected InfoLED from the left will be matched with either a previously detected InfoLED or a discarded InfoLED. For example, I highlighted a possible match in red. So for example, in this case, InfoLED 1 is matched with InfoLED history 2. InfoLED 2 is matched with previously detected InfoLED 1. And then InfoLED 3 is matched with the discarded InfoLED, which means that we think this InfoLED is probably a false positive, so it should be discarded, and so on and so forth. So we assign the distance between detected InfoLED and previously detected InfoLED to be related to their distance, and then we assign the distance between detected InfoLED and discarded InfoLED as a constant value to avoid unnecessary discard of detected InfoLED. And this is basically a bipartite matching problem, and we can solve it efficiently using a max flow. So now we have a consistent tracking of the InfoLED. We need to decode the information from the InfoLED. For example, this is an example signal might be the InfoLED might send, which is sending the data 101100. Here we might encounter a problem of misalignment between the sampling clock on the camera and the clock inside the microcontroller. So, for example, in this case, the vertical line is the sampling time of the camera. Okay, and now what we receive is basically 2 high. This is good because we can receive 2 high signal, 2 low signal, 4 high signal, and then 4 low signal. And we can easily decode it as 101100, which is good. But when the sampling frequency of the camera is misaligned with the LED, you can see the vertical line is shifted by half a cycle. What happens is there will be a lot of samples that is dangerously close to 0. Which means that, especially combined with the noise of the camera sampling and many other factors, we might get an incorrect signal in that case. So in this case, we may decode it as 1 to 3 high signal, depending on what we receive on that position really close to 0. 1 to 3 low signal, 3 to 5 high signal, and 3 to 5 low signal. So we may receive 3 frames of a given signal, which we cannot reliably decode. We don't know whether it's 1, 0 or 2, 0. So InfoLED actually decode the information by estimating the moment when the signal go across 0. And then instead of counting the number of positive frame and negative frame, we compute the time difference between each crossing. So this signal can be correctly decoded as 2 frames of two frame of length of high signal, 2 low signal with the length of 2 frames, a high signal with a length of 4 frames, and a high signal with a length of 4 frames. And then we can reliably decode it as 101100. So with this entire pipeline we designed, we can robustly detect and track and decode multiple InfoLEDs at the same time at 240 frames per second. Okay, and next I'm going to talk about a few user studies we have done to evaluate this system. So we evaluate the performance. We first evaluated the performance of the InfoLED with 12 participants. We asked each one of them to use the InfoLED scanner from 1 to 7 meters away from the InfoLED, and in 3 different lighting conditions, including outdoor, office, and dark. This is data we collected. As you can see, InfoLED can be reliably decoded up to 3 meters in outdoor conditions, 6 meters in dark condition, and 7 meters in office conditions. With another experiment investigating the human readability of InfoLED, because we claim that InfoLED can work with existing indicator light without disturbing its original functionality. We asked participants to identify color and patterns of InfoLED in different environments, and we also asked them whether they noticed any flickering. This is data we collected, and as you can see, there's no accuracy or speed difference in identifying pattern and color in both InfoLED and baseline conditions. Users can sometimes tell the InfoLED has extra flickering, but they don't notice it most of the time. We also ran a third experiment evaluating the overall preference between InfoLED and AR tag, which is a baseline condition. We recruited 12 participants, and we asked each one of the participants to use InfoLED and AR tag to complete a series of tasks with IoT devices. In InfoLED condition, appliances use indicator light to transmit positional and debugging information. In AR condition, appliances use AR tag for positioning in AR. We asked them to solve a problem with their IoT device, control a light switch, and configure logic between the smart button and the smart switch. This is the feedback we gathered. And we can clearly see that InfoLED has less physical demand and frustration level for the user. It also has, the user also rated InfoLED as have better appearance, tracking accuracy, and overall preference. We also gathered the task completion time in InfoLED and baseline condition. As you can see, participants in the InfoLED condition completed tasks 2 and 3 faster in the InfoLED condition, and completed task 1 longer in the InfoLED condition, but the result is not significant. We think this is possibly due to, because InfoLED can transmit extra debug information, the app will automatically ask them to view an optional video tutorial showing how to fix this problem, which costs longer than the baseline condition. Finally, I'll talk about the application of InfoLED. We think InfoLED can be used to control appliances due to it can recognize the device from really far away. It can also be used to debug applications because it can carry extra debug information. In this case, your user's smart button is not working. The user scans the button, and the app shows that the Wi-Fi is not connected. And then the user can simply deploy the correct Wi-Fi credential by tapping on the app. Finally, InfoLED can be used to configure appliances. For example, in this case, the user wants to configure the smart button to control the smart switch. What the user needs to do is just scan the smart button and then scan the smart switch and then drag a line which establishes control between the button and the switch. After this configuration, the user can just press on the smart button to control the smart switch. Finally, I want to do a simple recap of this entire system. So I want to emphasize that without our unique encoding scheme, InfoLED can send arbitrary payload up to 44.4 bits per second with normal brightness LEDs. With our unique GPU processing pipeline, InfoLED can scan from 7 meters and track at 240 frames per second. With our unique tracking algorithm, InfoLED scanner can track up to 7 LEDs at the same time. So, InfoLED provides a precise and aesthetically pleasing tracking method for appliances to support versatile interaction in AR in different environments. You can find our project and source code here. And I strongly encourage you to see my demo this afternoon and try it out yourself. That's all.
Thanks. Yeah. We'll take some questions now. No one has any questions.
With some products having pulse width modulation to perform dimming capabilities in their LEDs,
sorry,
the dimming capabilities over time in LEDs on some appliances, they have dimming capabilities over time.
Oh, right, yeah.
Does the technology work at the same time of that dimming?
Yes. So we've done an experiment evaluating users' ability of recognizing different colors and patterns, right? So the patterns we have is fast blinking, slow blinking, and what you have said, we have a breathing light condition where the light is basically going darker and then brighter and then darker and brighter, and it still works.
Good. Yeah. I mean, I've got just a quick kind of clarification question, actually. You mentioned the packet error rates on one of your slides, and I'm just kind of curious. So that's the packet has to be 100% recognized for that to work,
exactly.
right?
Yeah.
Okay. So this is your So
this is the bit error rate, which is like the error rate of a single bit transmitted, and then we design our packet length actually according to the bit error rate, so that to maximize the correct transmission of the entire packet.
And so, have you considered like applying any form of error correction to check the values to maybe improve the reception rate?
Yeah. So we have a 2-bit error check. So I think theoretically we can correct up to 1 bit of error, and then we can detect 2 bit of error. But if there's more error than that, we'll just fail, and then we wait for another transmission. Since the transmission is pretty fast, the current packet transmits at like 0.5 seconds per transmit. So just wait for another 0.5 seconds, you'll get another packet.
Thank our speaker. Oh, we got
very nice talk, first of all. Have you tested, because since you're encode data in a time domain, have you tested on like really big data? And how does your system perform on that?
Sorry, what do you mean by big data?
Like if the data you're trying to transmit through the LED is like very big.
You mean like a really long packet?
Yeah, like a really long packet.
So we didn't specifically test this because we think InfoLED is used as like an AR positioning method. If this is a smart appliance, the appliance can establish a better data link. Like Wi-Fi or Bluetooth after the AR app knows where the appliance is. But I think this will work with a longer data transmission. It just won't be the best method comparing to Bluetooth or Wi-Fi.
Thanks once again.